So thanks, Joao, for the introduction. In fact, we have a lot of things to do, and that's why also our presentation will jump through the different topics quite fast. So I have the honor to present the MTech project and all the consortium today here in Brussels. So first of all, what's the consortium about? So we are 10 partners spread across Europe, trying to fulfill all the objectives that we proposed to do so. So we are in the third year of the project, so we are trying to finish everything up, to reach the targets, to have already hardware available, already hardware on the test bench, trying to validate all these simulation efforts that we did at the beginning and verify it and validate it on the test benches. So what are the main objectives? So we are dealing with we are combining two different e-motor technologies in one project to cover more or less various segments that are possible. On the one side, as you can see here from the targets, we have the radial flux in-wheel motor, where we, on the one side, increase the performance, high torque density and high efficiency targets. And on the other side, the axial flux motor, onboard motor, where we also increase the performance and the efficiency. And in addition to that, as Joao already mentioned, we have another topic to deal with, and that's the circularity topic. So reduce the rare earth resources and materials in the meanwhile, so up to 20% for in-wheel motors and up to 60% for axial flux motors. Well, that's the topic of circularity we are handling as well. So on this topic, LCA, LCC methodologies also taking into account the remanufacturing and recycling topics as well. So we are also investigating in remanufacturing, recycling, permanent magnets and so on. You will see it afterwards. And in addition to that, to have an affordable electric vehicle on the market, you need an affordable e-motor. And that's why also the cost topic is very, very big in this topic as well, because you cannot penetrate the market with a high efficient motor with reduced rare earth materials, but a higher cost, because no one will be there to buy it from the market. So achieving cost less than €6 per kilowatt for in-wheel motor and about €5 per kilowatt for an axial flux motor. Also and I mentioned it already, the test and simulation we do upfront is also one part of the project. So for digital twinning and some kind of distributed X-in-the-loop solutions, we'll present it afterwards, to accelerate this testing of electric drive and complete powertrain solutions on testbed, covers vehicle corners or complete drivetrains. But let's step into the presentation of the results. Be quick, so I'm already late in time. The in-wheel motor on the one side is developed by ELAFE together with our partners from Polytechnicum di Torino and University of Bath to improve the energy efficiency by extending high efficiency operating regions. And that's more or less solved through an e-gear, a mechanical switching e-gear that's directly integrated, you can see, directly integrated in the in-wheel motor application. So to this fact, you can see the calculated motor efficiency maps presented. So on the right side, see without e-gear, on the left side with e-gear, to extend more or less the possibility to have a higher motor efficiency or speed torque ratio available to cover certain control strategies. As well as the direct cooling integration to increase the torque and power density in this in-wheel motor application. We have it already on the test bench at ELAFE and try to validate all the topics that we have addressed so far and upfront modeled and simulated. On the other side, axial flux motors are also their performance targets and challenges, so high power density reduction, and that's a heavy reduction of more than 60% for rare earth volume, so rare earth content, and heavy rare earth content at 0.3%. So they are also exploring innovative cooling systems and manufacturing methods so that it becomes very easy to manufacture and build the axial flux motor to the specific application. So develop also indirect cooling methods, explore different rotor designs to improve the drag losses. And on the other side, innovative manufacturing methods for enhanced components installation and improved assembly process, and also in mind to have some kind of disassembly process in mind to get back the permanent magnets and the rare earth material. Let's jump a little bit to circularity topics, from technical to more circularity topics. So we are preparing new end-of-line scenarios. What we are trying to evaluate and calculate with LCA and LCC realistic dismantling procedures to allow the permanent magnet recycling. So therefore, at the moment, the urge of permanent magnet, the material is rare, as it says in the word, so it's not available on the market. So trying to get the material back with the recycling processes. And there is, as always, different designs of e-motors, different possibilities to reach this permanent magnet. So we need a solution that is more or less free and open to recycle any kind of e-motor technologies and designs that we have. So our urban mining concept, as you can see here, is thermal demagnetization, sorry, to bring it out, mechanical separation of rotor and stator, so the copper-rich friction and more or less the iron and permanent magnet section to separate them, do some kind of reductive smelting, and what we have is a rare earth slag with up to 20% of Nd2O3, which can be used to refine it and recycle it and made out more or new permanent magnets. Also a good topic, and Henry told me he will be the last presenter of today, that it's not useful to present a lot of formulas in a presentation, but they are very small, so please, please forgive me. So also innovative control strategies. So we have the possibility in the project with the onboard motor as well as the in-wheel motor to really dig deeper into these innovative control strategies, because we have a lot of different situations, capabilities, different segments to fulfill. What you can see here on the right side, so route-based gear shifting strategies, so where we have this E-gear switching from series to parallel. We extend the possibilities for the e-motors. We can, on one side, do an energy optimal gear shifting using some kind of pulse and glide approach. Yeah, sorry, missing some pictures. But on the other side as well as brake blending controller with energy efficiency optimization. So we are really getting up to vehicle, so vehicle control to get the energy consumption down and to be more efficient overall. And that's what we achieve, at least in the simulation, 3% energy efficiency increase compared to the series strategy in WLTP drive cycles. And last but not least, virtual and experimental testing. I already pointed out that we have this X in the loop concept, and we enlarge it to an X in the loop network by real-time networking complex testing facilities. So we're also very happy to have 2 partners in there which are capable and have the same test tricks available. So as you can see on the one side in Germany, so Technical University of Ilmenau has on their side the brake hardware in the loop testing, so hydraulic brake system available, as well as the complete vehicle model and control strategy for that. And on the other side, the powertrain test rig, where the powertrain is mounted on the test rig, is situated at the University of Surrey, and they are communicating in real time and testing all these different components on different test rigs and have the data set for a whole drivetrain at the end. So this is something we are really pleased to have. Now let's come to the mid and long-term expected impacts. And of course, if you have deeper questions on these topics I presented, I know I was very fast in presenting all these topics, please do not hesitate to contact us. We have a homepage, we have a LinkedIn account, so please contact me also directly. I will forward you to the experts if you are interested. So, mid to long-term expected outcomes. So on the technological side, so high efficiency, affordable in-wheel onboard electric motors. So we are at the end demonstrating really on the test plan 20 to 25 energy loss reduction along driving cycles, starting with the WLTP, of course. Economic, so providing cost reduction on all these topics, and that's more or less one of the hardest points to reach at the end with all these other topics in place, and decrease the rare earth usage of 20% for in-wheel motors and 60% for onboard motors. On the scientific side, also new validated research methodology, virtual sensing, so virtual temperature sensors in e-motors or an electric powertrain overall application, LCA, LCC methodology, and of course smart e-motor control within e-corner and e-axle framework. And of course, realistic test bench environment, so automotive quality level demonstrated. What's the impact? Start with to gain a broader market penetration. It is the need for new generation electric motors is there in place. So we have to consider recyclability, reduce the amount of rare earth materials, very cost critical, and a full life cycle assessment, including, of course, recycling, remanufacturing. So the market penetration, what we are at the moment aiming for, and we are good with the outcome of the project, because at the moment the annual growth rate is more than 30%. So there is a high demand of in-wheel motor, new technology of in-wheel motor and AXIal flux motor technologies on the market. And with 2 partners, with 2 different concepts, we are hoping that this will work out at the end. Ecosystem, and that's a very good point, and I hope all the other projects also were presented. We have a close interaction with the Vivid ecosystem. We have 4 sister projects. We have the Evolve cluster where all these other projects are also involved to really create a critical mass for research and innovation and real uptake of the research outcomes, of course. Social, increase the e-motor performance and reduce rare earth content is contributing to a more sustainable transportation and positively impacting the acceptance of the electric vehicle. As we discussed yesterday, this was quite fruitful. There's a missing acceptance at the moment, but environmental also trying to improve the high efficiency reduction of rare earth material. Thank you very much for your attention. I hope I get some glances from our project, and please contact us if you have further questions. Thank you very much.
So, as we discussed before, please keep your questions for the end, where Damian will share the Q&A questions. So, the next project is MAXIMA. Client Stefan please, to present. So modular axial flux motor for Automotive from Stéphane Clanet from the Artemetier Institute of Technology from Lille.
So I can...
Yeah.
Okay, can I come back? Okay. So thank you very much for your kind introduction. So I'm Stéphane Clanet, Professor of Electrical Engineering at Artemetier. So I will present you the MAXIMA project. So first, the presentation of the consortium. So in the consortium, in fact, we have a car manufacturer, Stellantis. We have a electric motor manufacturer, e-motors. We have also two producers of soft magnetic materials, which play a key role in electrical machine. So OCAS, in fact, it's the R&D center of ArcelorMittal, so for electrical steel. And Oganas also with a manufacturer of powder for soft magnetic composite materials. We have also a company involved in the recycling and also in the manufacturing of permanent magnets. And finally, we have a company expert in the design of electrical machine. About the academic partners, so there are UPC, so from Spain, with a specialist in control electrical machine and thermal management. We have also UTCN, they are working on the design of the electrical machine. We have also VUB, specialist in life cycle analysis, and finally us, specialist in the life cycle analysis, digital twins, and so on. So the project is a 4-year project, and the budget is about 5.6 million. Just one thing, so we cover, so it's something that I think it's important, we cover almost the full chain from manufacturing to recycling of the electrical machine. So about the KPIs, so the aim of the project, so it has been presented before by Martin, and I think my colleague will repeat it, because in fact, in the call it was very clear what KPIs we have to reach. Sorry. And so, but the number of KPI was not sufficient, so we proposed to add other one. So one related to the efficiency and one related to the torque speed characteristics of the specification made by Stellantis. So some preliminary results. So just a few words about the timeline of the project. So in fact, you have first the design of the digital twin. I will explain what we mean by digital twin in our project. We have also the design of the electrical machine. So the design now is done, so after 2 years. And what I should mention is that the design was made at the same time as the manufacturing process flow. Because in fact, as it was said by Martin before, we have to reach, or the cost is limited, so we have to design an affordable machine for the core market of automotive. And so this is why we have to take care during the design of the manufacturing. And so this is why we have this kind of loop between the design of the machine and the design of the manufacturing. So now the design is done, and we are starting to manufacture the prototype to verify our concept. So in parallel, we have we work on the dismantling and recycling of permanent magnet, and also we have a continuous activity about life cycle analysis. So about the design of the electrical machine. So I'm sorry, I cannot show you some pictures, some design of the electrical machine, because we haven't decided yet what kind of information we can disclose or not. So we'll just talk about generalities, in fact, related to the methodology we have employed and the different structures we are working on. So we have considered different kind of electrical machine as it is showed on the right side. So for the stator, different kinds of windings, so concentric windings or concentrated winding, sorry, or distributed winding. For the rotor, we have considered surface permanent magnet rotor, or interior motor, or V-shaped motors, V-shaped rotor, sorry, and also different configuration related to the association of the rotor and stator, so either dual rotor or dual stator. And the methodology was is shown globally on the right. So it means that from the design of the electromagnetic design, we extract some information related to the losses, to the force, and so on. From this, we are able to do some simulations simulation of the thermal behavior and the mechanical behavior. From this, we extract some information. We are, in order, for example, to design the thermal, the cooling system. And then we come back, we look at the KPIs, and we see if we reach or not the KPIs, and so on, and we iterate like this. So some results about the life cycle analysis. So on this picture, so what we did, in fact, for each design, we evaluated the life cycle analysis. So in fact, here you have what is considered, it's only the manufacturing and the usage of the machine. So what you can see is first that if we consider the manufacturing, what is important is mainly the coil, so the copper, the permanent magnets, and the motor production, so the assembling, in fact, and also the housing related to the aluminum parts. If we look at the usage, so it's the brown block, in fact, you have an error bar, as you can see here, and this error bar is related, in fact, to the mix, the electricity mix that is used. And what is interesting here is that if you have a very good electricity mix, it means that the electricity is produced by renewable energy or decarbonized energy. It means that in that case, the usage has less impact than the manufacturing. Because usually what we think is that the manufacturing has a negligible effect here. It is not the case, but in fact, if you look at the top, so the top of the error bar, in that case, we can see that the usage, in fact, has the most impact, but in that case, the mix is mainly made with carbonized energy, fossil energy. About the permanent magnet, so as I said, the idea is to consider the recycling of the permanent magnet. So we have started here. So the idea is first to validate the process of recycling, and then also to manufacture permanent magnets that are well fitted for our application. So what does it mean? So it means that about the recycling, so first test was done, so we consider some permanent magnet scrap. So here it was a G44EH magnets, so provided by the company Automotive. And then we, not me, but me plus company, recycle so the permanent magnet. So it means that they have to remove the coating in order to have only the powder of the permanent magnet. Then you have a decryptation and a jet milling in order to be able to have the powder of permanent magnet. Then you have the feedstock production, the injection in the mold, and then the debinding and the sintering. So in the picture, you can see the green part that is made, that is obtained after injection. And on the right, the sinter part, so the permanent magnet by itself at the end of the process. So you can see that one key problem here is that the modification of the size of the permanent magnet So this is something that we have to, what can I say, to manage. So in order to be able to get at the end of the process the right dimension for the permanent magnet. And if you look at the performances we get at the end, I'm sorry, we get at the end, in fact, on the bottom here, you can see that the virgin materials we had a BR, so a residual remnant magnetic flux that is equal to 1 point. So we are not far away, in fact. What I should say is that for BR, so the residual magnetic flux, we are not far away from what was for our recycled permanent magnet, what was at the origin. But we lost a little bit about the coercive field. So it means that is something that we have to improve. But as I said before, the aim is also during the process to control what was said by Martin just before, the rate of heavy rare earth in order to get what exactly we want to get as coercive field, to avoid demagnetization inside the machine. So this is something that, and MIM+ can do that, so this is a very interesting aspect of the project. So about the digital twin, so I talked about digital twin just before. So what do we mean by digital twin in the project? So the idea is when you want to design a device, or in our case it's an electrical machine, so you consider high fidelity model, so numerical model in fact, to study the electromagnetic part, the thermal part, the mechanical part, and so on. Then from this you design your device here, and then you manufacture your device. So here for us, so this kind of high fidelity model is virtual prototype, what we call virtual prototype. So in fact, why virtual prototype? Because in terms of performance, so we are not far away from the performance we can get at the end on the real machine. But here, what we want to do, in fact, is a numerical model. So what we mean by digital twin is a digital replica of the real machine. So it means that it's how can I say, a device that is running, in fact, in real time, and enables you to get any information you want about the electrical machine. And in order to do that, the main idea is to start from the high fidelity model, to extract information. And so, for example, you can use model order reduction techniques and so on. And like this, you can get very fast model. And this model can keep you the possibility to have access to any quantity. So it means locally, the losses locally in the machine, not in the iron core, for example, but locally in the machine. So it means that for the thermal model, you will be able to provide more accurate information, and like this, be able to determine more accurately the temperature distribution within the electrical machine. And moreover, what is interesting also with this kind of approach is that you can find the right place for the sensors in order to extract the right information, which enables you to recalibrate, because the characteristics of the machine will evolve with time, will change. So the idea is to recalibrate the model. So here you have a complicated pictures about the digital twin. Is just to say that the digital twin is in fact in the middle. So you have the control board, in fact, on the left. So it's a classical control board, a standard one. But this control board, we'll have some exchange with the digital twin in order to extract the relevant information in it. So this is something that is quite interesting. So about the impact, so it was said by Martin just before, and it will be said by my colleagues just after. The aim is to design an affordable electrical machine. So, and the target is for us 6 euros per kilowatt. So using the digital twin, we hope to be able to increase the efficiency by 2%. So in fact, we will have access to all information, as I said, and also the losses, for example. And so we will be able to control the electrical machine in order to minimize the losses and increase the efficiency. About the CO2 emission, what we can see is that according to the results we get now, and I didn't mention it at the beginning, but we have a reference machine that is on the market, and we have chosen what was on the market in 2020. And what we can say is that we will be able to reduce the impact by 32%, until now, what we were able to do. And something that I think is really interesting for the future is the notion of digital twin. As I said before, we will use the digital twin mainly to control and to improve the control of the electrical machine. But what is interesting with the digital twin is that you will get a lot of information during the life of the electrical twin. So it means that at the end of the life of the electrical machine, you will be able to evaluate the health of the electrical machine and if it is possible to reuse it or not, and also to determine if the failure, what kind of failure, when it happens, and so on. And also, this kind of digital twin can be used for hardware in the loop. So in order, for example, to evaluate the power converter, the quality of the power converter, and so on. So what we have done for the digital, what we'll do for the digital twin is just a beginning, and I think that there is a lot of things to do in the future based on that. Thank you very much for your attention.
Thank you very much, Stefan. So next project is going to be HEFT, and is going to be presented by Fernando Garramiola, please, from the University of Mondragon. So HEFT, novel concept of a low-cost, high-power density and high-efficiently recyclable motor for next-generation mass-produced electric vehicles. Another quite long title to show the...
This one, just to pass this one. Okay, thank you very much. Okay, the first thing, just to thank you for inviting us to present the HEFT project just here in the conference. Yeah, we have a long title because we wanted just to be there all the important things of the goals of the project, of the HEFT project. Okay, so it's based on one idea that, I mean, can be an hypothesis if you prefer, that in case of power density and torque density, the permanent magnet machine is the most suitable one. Yeah. So based on that, what we propose is different innovative challenges in order to improve the machine. Yeah. And we are going to do in two different ways: in the motor configuration and in the material development. About the consortium, that I mean, we have in the consortium universities, we have industrial partners, and we have research centers. Yeah? So the coordinator is Mondragon University, that is involved in the rotor design, is involved in validation and in the assembly of the motors. Yeah? We have industrial partners. We have Sumibe, that is responsible for the magnet manufacturing, magnetic, and Subive for the material development, for example, for the wear molding for the magnets, to make AXIal extraction of the magnets. We have a research center, that is Sicarland, more focused on the control strategy. And then we have the University of Bologna for insulation issues, Leuven for LCA, and Nottingham for continuous winding, for the stator of manufacturing. Yeah? Apart from that, until last December was a tier one with us, GK and Automotive, but due to internal business strategies, they left the project in December. So I have to say that we are looking for people just to take part in the advisory board, yeah, just for OEMs. Okay. Related to the project, it belongs to the call next generation electric vehicles components. Yeah, it starts in December 2022, and the end is in May 2026. We have more than 3 million of funding from the European Union. As I think that I don't know if all, but at least the most of the presenters of this session, we are partners of the Evolve cluster, and we collaborate in activities related to communication and dissemination. So in HEFT, we have two main objectives. Yeah? The first one is related to the development of low-cost and higher efficiency and higher power density motor, yeah? And always with a mass-produced level, let's say. Yeah? And the second one is related to the development of resilient long-term strategy for the rate elements. That is a problem that nowadays we have. Yeah? For that, we have presented different KPIs that we are going to validate during the project. Yeah? And at the end of the project, I will show you some of the numerical values of the of some of the KPIs. Yeah? About the results, I will explain the results based on the key exploitable results that we proposed at the beginning of the project, and we'll say later on which one is the state of that result. Yeah? So initially we proposed 4 key exploitable results. The first one is related to the next generation of e-motors. The second one is related to the magnets, both for recyclable and less magnets with less rate elements. The third one is for the rotor and stator subsystems, because we have some challenges in the design of these elements. And the last one was just for the reusing the magnets and recycle processes. Okay. So based on that, on the right side, you have the project outputs. So all the things that we are going to, let's say, take from this project. Yeah? And we have things as a digital twin. We have a multi-barrier rotor topology. We have the continuous 24 stator. We have new coiling systems. Okay. So starting with the first curve, yeah, the next generation e-motor. On the picture, what you can see is what actually we have designed. Yeah. So we have designed 2 prototypes for 2 different segments. So the idea is just to have one. Let's say, one design, yeah, for the AB vehicle segment and another one for the CDA vehicle segment, yeah. So already we have the designs, yeah, designs are finished and frozen, and with that, as you can see, at the moment, the results that we have, they are promising, very promising, yeah. So we have savings in weight, we have savings in volume, we have savings in the quantity of rate elements, and we improve the maximum power, yeah, and we improve the maximum continuous torque too, yeah. Apart from that, in both cases, we have a power density per kilogram over the 7 kilowatts per kilogram. That is really challenging. Related to the second curve, yeah, the permanent magnets with rate reduction and recycled magnets, the same. I have divided in 2 segments. Yeah? So in the case of the first segment, for the AB segment, the magnet grade that we propose in the design is the N38H. So already we have arrived, let's say, yeah, to get the performance of that magnets with cerium-based magnets, with grain boundary diffusion, and with recycled magnets. So both the strategies, yeah, the one that you can see on the picture on the upper side, the recycling one, yeah, and in the case of the cerium substituting the neodymium, in both cases we arrive to the performance of the N38H. In the case of the CD, yeah, we are trying to decrease the quantity of dispersion in the magnets in order to arrive to a grade of N42, yeah? And in this case we are close, but we haven't arrived yet. In any case, you have on the picture too the remanence and coercivity that we have at the moment. Yeah? In the case of the Curve 3, advanced rotor stator subsystems, we have different innovations. The first one is related to magnet overmolding. So with this magnet overmolding, that allows to arrive to higher speed, and apart from that, it makes easier destruction of the magnet. Yeah. Apart from that, we have a plastic housing. So with this one, we can reduce the weight of the motor, yeah, and we can decrease the carbon footprint too, yeah. Then we have, let's say, a novel oil cooling, a centrifugal oil cooling in the rotor too, which allow to improve the continuous performance. Yeah. In the case of the stator, as I have said before, we have mainly two important points. The first one is the continuous winding for the stator manufacturing. Yeah. So in this case, it allows to have a higher quantity of conductors in one slope. Yeah. And as a consequence, I mean, we can decrease the losses in high speed. Yeah, it makes that the efficiency is better in WTP cycle, and apart from that, we can reduce the packaging of the stator. Yeah, another innovative challenge in the stator is that we have a jet oil cooling, and with that, I mean, we can kit the jacket. So with that, we have a reduction of the weight of the motor too, yeah? And obviously, we have an improvement in the continuous performance. In the case of the Curve 4, yeah, process for dismantling and reuse and recycling magnets, we have already extracted some magnets from the rotor. So you have on the left side, I mean, the tooling that we have already built, yeah? We have just one press for that. And the process is quite simple. It's more simple that you can think. Yeah. So what we have done is we have hit the rotor. Yeah. We have hit 300 degree during 1 hour. With that is enough just to degrade the adhesive that we have around the magnet. So once the magnet is cold, yeah, we extract with the press and the tooling. Yeah. You can see on the right side, on the upper side, the magnet after the extraction. Yeah. So they are complete. I mean, they are not broken. We have some dirty parts due to the adhesive material, but after the cleaning that you can do with the mechanical of, as I saw in this picture with a chemical process, is with acetone. Yeah. We can clean the magnet. Later on, we have magnetized the magnets, and we get more or less the original performance of the magnets. Yeah. So related to the impact, at the beginning of the project, we proposed the curves that I have already presented. They were linked to the outcomes of the call. Yeah. And to the zero emission road transport impact, yeah. And related to this one, we propose some specific objectives, yeah, in order to show the advance and the contributions of the project, yeah. So in the case of the first one, there is more related to design. I have to repeat it to the design, repeat to the mass production. So we have two innovations that they are running at the moment. We have the stator continuous manufacturing that we are with trials at the moment, yeah. And we have the design tools to maximize the KPIs that is already finished. It's the tools that we have use in order to design the rotor properly, depending on the requirements that we had. Yeah. In the second case, in the low cost, but we are working with the idea that our motor is going to be supplied with batteries with 800 volts. Yeah. So that allows us just to go to higher speeds and decrease the losses. And apart from that, we are using the digital twins, yeah, and optimize these controls. In the third one, we have already running the both routes. So on one hand, the recycling, so we are able to manufacture magnets based on recycling powder. Yeah? And with that, we have just the performance suitable for the AV segment. Yeah? On the other hand, we have the reuses magnets, so we have already extract magnets from a rotor and use the magnets, yeah, for the AV segment too. Okay, and finally, in the case of the European job creation, that is an incipient task at the moment, yeah, but we think and we want to show with HEFT project that we are able to build electrical machines in Europe, yeah, completely electrical machines, yeah, starting from the magnet to the complete motor, yeah, and apart from that, we think that in the case of business, we can generate more business based on the recyclability and reusing of magnets. And just to finalize, I wanted just to show you some data related to the KPIs based on the designs. So as you can see in the picture, yeah, the motor cost reduction is over the 25%. We have the losses, we decrease 20%. We get continuous torque much higher than the ones that were called, demanded in the call, yeah. And in the reduction of rider elements, we are close to the 20%, yeah. That's all. I didn't want to add more information, but just I want to say you, yeah, that the information related to the designs, they're in public the libraries, so you can check them, and the same in the case of the extraction of the magnets. Thank you very much.
Thank you very much, Fernando. So we go to the next, so the fourth presentation. So we will have VOLTCAR, and Jenny is going to present. I don't dare to say your family name, sorry. So VOLTCAR, design, manufacturing, and validation of ecocycle electric traction motor. So Jenny from VTT, the Finnish Institute of Technology, please.
Thank you very much. Thank you very much, Joao. Indeed, my name is Jenni Pippuri Mäkeläinen. It's a bit difficult name to pronounce maybe but that it is. And thanks a lot for the kind introduction, and thanks a lot for the opportunity to present the project today. So without further ado, let's go to the overall project presentation. And we can first take a look at the consortium and then a bit of the objectives. And here you can see the consortium and the consortium key figures. So we have altogether 12 partners from 6 countries. You can see that we sort of have a little bit of cluster in Finland. We have 3 partners from Finland. Then we have another cluster in Belgium. Again, there we have 2 partners, 2 partners from Germany, 3 partners from Slovenia, 1 from Cyprus, and 1 from Ukraine. And I would say I liked very much when Stefan from MAXIMA said that they cover the whole value chain. We do not maybe cover the whole value chain, but we have key players from the design to the manufacturing of the electrical machinery and also the testing the electrical machinery, without forgetting the validation activities, virtual and actual, like testing validation activities. The grant amount for us is nearly 6 million euros, and you can also see the project webpage there if you want to learn something more of our project. And then about the objectives. At this stage of the session, it's pretty difficult to say anything new about the objectives because the call topic was very, very specific. We had a very clear target to improve the future electric traction motors in terms of their efficiency, reduction of rare earth element contents, and also to decrease the size of the motor. But I would also like to emphasize, I think that Joao already said it, that none of these targets is difficult as a one single target. So you can definitely make a very efficient electrical motor. You can definitely reduce the amount of rare earth permanent magnet material used. And again, you can definitely reduce the size, but doing these all at the same time is rather challenging task. But okay, we all are now here to do that. And the numeric targets are now very similar to the other projects. So when it comes to the specific power, we are targeting at the more than 7 kilowatts per kilogram target. So that's about the classical motor design. So improve efficiency, reduce rare earth element content in the permanent, or by the reduction of the rare earth permanent magnets, and then also make the motor more compact. And then the second one is for VOLTCAR, is development of the circular technologies. So we want to enable efficient recycling of the rare earth permanent magnet material. Furthermore, we want to demonstrate this kind of a cost-efficient motor, and the cost efficiency was denoted very clearly in the call topic again. So we need to reach the level of under 6 euros per kilowatt hour at mass manufacturing levels. And also one important target for the VOLTCAR project also is the testing and validation, because otherwise we cannot prove we cannot prove that we reached the targets that we set to ourselves. And then about the results, I have altogether 5 slides of the results. They are selection of some recent advancements, and you can of course come ask questions and so forth, as the other presenters already said. We are available here for the discussion then. So then about our proposal, what we are aiming to do, what are the key things that we are aiming to present. So we are here concentrating on the radial flux high-speed permanent magnet synchronous reluctance motor technology. So this is a quite classical one, if I may say so, but what we are aiming to do, that we are elevating the speed of the motor a bit above the levels of the present traction motors at the market. And here you can see that the peak the power, the continuous and the peak power for our primary final prototype are 120/210 kilowatts. The speed is, the rated speed is around 12,000 RPM, and the maximum is 30,000 RPM. The DC voltage level is set to 800 volts. One of the key elements in the reduction of the size is the speed, but also the direct liquid cooling of the windings. So this is maybe something a little bit innovative in this project as well, that we really try to cool the windings as efficiently as possible, as close to the origin of the losses as possible. And then the full assembly, it includes a gearbox from our partner and also a silicon carbide inverter from our partner. And if you want to know more about the specification and requirements and the driving cycles that we are considering, you can refer to the public deliverables 4.1 and 4.2. And then on the, here on the picture, you can see a bit of the pathways of the project with which we try to go towards our targets. So we have the design and prototyping, the eco-design approach, the digitalized motor, and the validation. And you can there also map a bit the roles of the partners. So we have Heatriad done for Seritron, LUT, and Borg-Warner working on the design and prototyping. Eco-design approach, there is Kremenchuk, VTT, and Collector. Digitalized motor, we have Bosch, KU Leuven, and validation, we have University of Ljubljana and Siemens. And of course, this is so interconnected activity, this kind of a development, that many of us are contributing in several topics. But these are our key topics for the partners. And then about a little bit of the design and prototyping. So here you can see a little bit more of details of the prototype development and the key choices that we have made. We have also realized it very, very early that when you are trying to scrutinize the motor design from many corners, you need to use very efficient simulation and modeling tools. but also you need to confirm the manufacturability of the solution at different stages. So not only that you need to carry out a quite elaborate computational optimization, you need to at the same time consider that if this is manufacturable, how this is manufacturable, how expensive it's to do this and that solution that we are now going towards to. And then about a little bit of the innovative elements. I mentioned already the direct liquid cooling. It also requires thinking about how the liquid is arranged to the place it should be, what kind of insulations are needed. We are going with the hairpin winding technology. Then another important aspect in the motor manufacturing is that we are using these baking varnished lamination stacks, and this means that we don't need to introduce welds to the lamination stacks, which also contributes to the decrease in the losses, because every kind of tooling of the electrical steel sheets actually deteriorates their performance. And if you like to know a little bit of more details, you can refer, for instance, to the ISEM 2024 article. And I also wanted to put some key figures to make this hopefully a bit more interesting for the audience. So we have made some design choices. I have said that, okay, we have made some design choices in some webinars before also, but now I'm quite confident that now we have made really the design choices, and this is it. So there you can see the number of pole pairs. It's 3 standard 3-phase winding, but I think it can be quite interesting for you to see that the stator stack diameter is about 15 centimeters, and the stack length is 11 centimeters. So you can imagine it's of size that you can hold in your hand. At least one of our colleagues in the project was able to do so, and then the mass, including the frame, we are about in the target of 17.8 kilograms, and it includes now the housing of the motor as well. And then about a little bit of the eco-design approach. Again, quite specific nature for the call, quite similar topics in the projects. And here we are, like also as other projects, we are of course using the life cycle assessment or analysis to understand the impacts of the design choices that we make at different stages of the motor lifetime in regards of the energy consumption, emissions, costs, etc. And also the life cycle costing helps there a lot. And we have created this modeling chain where we do first the electromagnetic analysis of the motors to generate the needed efficiency maps. Then we carry out the vehicle level system analysis to understand how much energy is consumed during the lifetime of the motor in the vehicle. Then we of course collect a lot of data from other sources of the manufacturing and other things in order to carry out the LCA analysis in a sufficient manner. And here you can see a couple of examples in the bottom. So there is the manufacturing cost for 3 designs. And I guess you all can guess which of these motors has the least of permanent magnet material. Is it the A? Maybe not. Maybe not B, but it's the C. So definitely if you get rid of the permanent magnet material, you can reduce the cost, and then you get rid of the rare earth containing components altogether. But there is a price to pay, because with the permanent magnets, with the rare earth permanent magnets, you can improve the efficiency in very efficient manner, and you can see it also in the consumption, in the energy consumption, obviously, and you can see it in the end of the day in the emissions also generated during the lifetime of the motor. So you can see that, okay, there are quite many contradicting objectives that you need to ponder between in these activities. And then another thing is that, and of course, we have contributed and given our input to this Le Mesurier project. And another thing that we are interested in, we are trying to enable the reuse of the permanent magnets. So not like taking the magnets out and using a lot of energy to extract the elements of the magnets to prepare new magnets, but we would like to take the magnets out and then use them in another application or in an automotive application if that's feasible. And for that purpose, we are studying how much force is needed to extract the magnets. There was a very nice result from the previous project, how they were extracting the magnets, but what if there is sometimes a case that you need to enforce the magnet a bit with some physical structure? So we are also studying the encapsulation of the magnets to make them strong enough to be able to be removed from the motor at the end of its first life, intact to be used in further applications. And for initial results, you can refer to the TRA 24 conference paper. And then I have still a couple of more slides, but yes, the digitalized motor, this is a very, very key element in all the projects because you can enhance the design activities, you can enhance the lifetime management of the motors with these activities. So we are trying with the digitalized platform in VOLTCAR, we are trying to include manufacturing elements, operation, dismantle elements, a little bit like even reaching towards like a digital passport way of thinking. So you would know what is in the motor, you could use the model to operate it efficiently, and then you could maybe at the end of the first life to utilize the model to understand what is, how can you recycle it and reuse it. And here is the one nice example of the platform and its developments to do the vibroacoustic analysis of an electric traction motor. You can refer to this ISMA 24 paper if you want to know some details. But basically, in this approach, you do an analysis of the forces in the motor. You do the analysis of the vibration characteristics and the acoustic characteristics of the same motor in frequency domain. And combining these two information, you can just simply multiplying these two fields, you can generate the pressure response and the sound response for the motor, and really hear by your ear that okay, how this motor is behaving in action. And then to speed it up a bit, since we don't yet have the motor prototypes, I will not go in very detail to the validation, but we are planning to do the back-to-back testing for the motors, X-in-the-loop testing of the motors. We have already this kind of a tabletop setup existing at the partner's premises to demonstrate that this concept that we are developing is working in practice. And also in this kind of activities, it's very important to do different kinds of like intermediate testing and analysis and measurements to confirm that you are in the correct track, especially in our case on the part of the windings. And I think I will get the red flag pretty soon, so I will now definitely go to the impact. So yes, so here are the, if you look at this one, so there is a clear need for less costly, less rare earth element content motors and less energy consuming motors. And our results are the motors, optimized processes, demos, a holistic platform, and so forth. And of course, we would hope that the outcome would be that for instance, the project partners would be exploiting these technologies after or part of them after the project. We would like this to be converted to the reduction of the cost of the vehicles. And in the longer term, of course, there are very big objectives to, you know, to reduce the emissions and be resilient in Europe and to be like contributing to the Critical Raw Materials Act and so forth. But on the next slide, I have maybe something a bit more specific that I would like to say. So Evolve cluster, you already know. You know it very well. We of course want to disseminate with them. We want to make our work like visible. But one very clear observation from the first years of the project is that if we would allow a little bit lower specific power, we could, by using an inexpensive materials, we could still more improve the efficiency. So this is maybe something to consider, that I understand that we shouldn't waste material, but if we would allow a little bit more inexpensive material to be used, for instance, electrical steel sheets, it would be much easier to reach these energy efficiency increase targets. And now I need to finish, so thanks a lot for your attention.
Thank you very much, Jenny. Just a second. Pipuri Mäkeläinen. Okay, so we now go to the new kid on the block, so the newest project. We will have Hendrik van Soepel from the Ghent University presenting CliMAFlux, circular design and manufacturing techniques for next generation, highly efficient integrated axial flux motor drives for electric vehicles. So, thank you very much.
Okay, thank you very much for the introduction. So I will present something of CliMAFlux, our project, and I will try to share my enthusiasm of this project with you today. So first I would like to say something about the consortium. So as you can see, we started 1 year later than all the other projects in the same call. This was due to the reason that we were on the reserve list. This also means that today I can only present the results of 1 year. So we will see quite preliminary results. Yeah, so the project is about 4.3 million euros and lasts for 36 months. And as Joao already mentioned, it lasts for 36 months. There are 9 partners of 5 countries, and we are also part of the Evolve cluster, you might all know. So really in the base of our CliMAFlux project was the AXIal flux motor technology. At Ghent University, we're already active in AXIal flux motor technology, particularly the ASA, the oxygen segmented armature machines, for 15 years. And together with AXIal, they have a track record in AXIal flux design and production of about 10 years. Of course, with AXIal flux technology in itself, you're not there yet. So therefore, we have Blue Ways, an SME working on power electronics in our consortium. And we would like to really work on a full IDU. So this means that we have an Austrian company, Start, working on the gear integration and the vehicle integration itself. Then we have some testing partners. So Theo Ilmenau is really doing activities in this project on testing, hardware in the loop, and all kind of this parts. And then we have Polito in Italy, working on longitudinal vehicle dynamics, and University of Firenze working on sustainability in our project. So these are really IDU-rated activities, so vehicle level, but we also want to showcase that AXIal flux YASA technology can be used in other applications, so fractional power applications such as actuators in EVs, and therefore we also have Tenneco Belgium and Tenneco Innovation in Spain in our consortium. So what are the objectives? Well, as for the other project, it's really working on AXIal flux motor technology, so high efficiency, high torque density, so the same targets that I've already seen today, so 23 kilowatts per liter and 7 kilowatts per kilogram. And also we set a target on efficiency, so we want to obtain efficiencies higher than 97%. So it's also about the integration of functionalities, so meaning electronics, motors, gears. So at the project, we aim to develop an entirely AXIal flux-based IDU, working, of course, with the new standard of 800-volt technology, meaning that we are using silicon carbide inverters and so on. So next, we also want to reduce the environmental impact of EV manufacturing, so mainly focusing on the permanent magnet, but also reducing the copper content in machines by replacing the windings by aluminum. This all is supported by a large set of activities related to digital twinning. both in terms of control optimization, but also in terms of design. So then I will present you some key results of our, let's say, first year of research within this project. So the first thing is about, how are we going to tackle axial flux IDUs? So for radial flux, we all know how to do this. And if you take a look at some concept 3A and 3B, everyone is quite familiar with them for radial flux. So we just have a two-stage helical gear set having parallel shafts. So this is quite common to be used in radial flux machines. You can still shift between the position of the inverter, but basically this is what we already do for radial flux machines. But for axial flux, there are additional advantages, like you have a more or less hollow machine. So you can take advantage of this by just continuing the shaft throughout the motor. And in this project, we consider two alternatives. So one with still using a helical gear, a two-stage gear. But the other one is also taking into account a planetary gear set, so a single-stage parallel gear set. And as you can see already in these pictures, they're quite different in terms of sizes. So the volume of the planetary gear seems to be the biggest one, but the integration dimensions might be beneficial to integrate them into a vehicle. So there in the project, we will further on elaborate on the different configurations and try to find out which one is the most appropriate in a B-segment car. So then the second topic we are investigating is something brand new for axial flux, but also actually for radial flux as well. So it's based on what is called EMSM, so the electrically excited motor. So it's an electric motor without any permanent magnets. But we still see there's some disadvantages because you still need the excitation power to hold the whole driving cycle. And this concept, and I think it's brand new, it's combining permanent magnets, so a small amount of permanent magnets together with an electrical excitation system. So in this way, this allows to reduce the permanent magnet contact significantly. It's possible to work with ferrite magnets even. And as you can see on the pictures, depending on the size of the magnets that are used, you can have some kind of offset of the magnetic flux, and you can make a variation on that flux by the excitation winding. And this is, it's new, so we are having a patent application on this at the moment. And depending on the amount of permanent magnets, you can really play with the efficiency. So most of the current motors, they're over flux, so this is just solved by us by using only a small amount of magnets and by introducing the excitation current. So in the high torque, low speed region, this means actually that we're going to need the additional excitation by the electrical winding. So that's definitely something that we need. But in the field weakening region, there this kind of machine is really, really nice. Because what do? We just take the flux by the excitation winding away, and we have a very small flux that allows us to go very high in speeds. As you can see, the permanent magnet content has a major impact on let's say, the region of best efficiency. So even the high permanent magnet content is still far away from what we know today as a permanent magnet machine. But you can see that even for very low permanent magnets, they're excellent in high-speed region. But by increasing the permanent magnet content slightly, you can see that this shifts more to what we call then the partial load conditions, in which actually there is a lot of efficiency to gain with respect to current systems. So this will be illustrated and worked out during this project. Then another aspect, and I think it's already mentioned by Jenny, so one key point is also speeding up. Speeding up an axial flux technology is not that easy because you have disks with quite some diameters. So getting high speeds is there really tackling the issue of centrifugal forces. For our high-speed concept, as presented in these slides, we aim two possibilities. So one is really working with mechanical fixation. So that's really nice in terms of sustainability and recyclability, because you can just take the magnets out after the product lifetime without having any chemical or thermal measures that you have to take. And the other concept is based on overmolding with the thermoplastic material, which is still feasible to recover the magnets after its service time. But as you can see, we're quite successful in, let's say, exceeding the 15,000 RPM limit with these motors, and even exceeding the 20,000 RPM with the overmolded version. Yeah. So also on this technology, AXIal, so the Magnox company, has a patent on this way of working on the mechanical parts. So then, as I mentioned, a lot is based on digital twins. So in AXIal flux technology, certainly for us, it's really about not percentages, but about percent points. And then you need very accurate models to predict the behavior of the whole system. So we do have these accurate models at the, let's say, power electronics motor level, but we should take into account the same level of accuracy without, of course, having the need for very high computational times. And there the University of Torino is assisting us in making AI-based, so actually it's more or less a neural network that is used over there to, let's say, to have the accuracy of the full-scale model without having to spend a lot of simulation time when doing vehicle simulations. And for instance, in the figure shown on the right, there is a tip-in maneuver, so just getting the torque to 60 Newton meters. And as you can see over there, then we're talking about the velocity of the speed of the motor and the speed of the wheels. Then you can actually see that the neural network-based model is performing quite well, and so helping us in modeling in an accurate way the vehicle dynamics and its impact on the motor. So these were the major topics that I selected today for you. And I would like to say something about the direct impact. So direct impact for us, of course, it's a new generation of AXIal flux motors with the efficiency demands that are asked, with the power density requirements, but also at the same time reducing the critical raw materials, in our case, mainly the permanent magnet material. Then, as I mentioned, the impact of this hybrid excited technology will also have a major influence on the future design of AXIal flux motors. So there, at first, it will be tested in the IDU, but we also have other applications and more actuators related topics. This brings me to the next topic. So the idea and the impact of the CliMAFlux project will also be that we're not investigating IDUs only, but also introduce AXIal flux motor technology in quasi-direct drive actuators, doing, for instance, active suspension, active camber, active 2, active steering, so all kinds of applications. There we also see a market for AXIal flux motors because of the high torque density, the low weight, and the excellent efficiency. The use of digital twinning, as I mentioned already, both in the control and the design phase, is a key part in our project. So there it goes even through the design phase by reducing the number of components. It goes having a higher recyclability rate. It's going to be faster design to production times. So all these things are mentioned, are taken over by either digital twins, either by existing framework, for instance, available at the University of Firenze, doing the life cycle analysis already from the early design point on. So, of course, this will have an impact also on our partners. So, at least for AXIal and making AXIal flux motors, this will directly influence their product portfolio. So not only IDUs, but also eventually these actuators. So since we are making an integrated system, also the electronic companies like Blueways and the system integrators like Start will also benefit from this new concept. We also are quite aware that we can make advancements in the vehicle acceptance. So AXIal flux technology was really nice, but so far it was only introduced, for instance, by YASA in the EMG models of Mercedes. But yeah, we are making sure that we can also use this technology in, let's say, B. Every person can afford, let's say, an AXIal flux motor at a competitive price. And of course, due to the fact that we are strongly reducing the magnet content, we're very resilient to magnet prices, which are quite volatile. And of course, we can also benefit or help us to obtain the required sustainability levels. So this was my presentation. I hoped I could share my enthusiasm. At least we have an enthusiastic team that is presented over there. So on behalf of my team, I would like to thank you all for your attendance during this presentation.
So this was the last presentation for this session. So now I will pass the session for my co-chair, Damian from the RWTH-Aachen, for your questions. So please, fire ahead.
Yeah, thank you. Yeah, from my side, thank you to all the presenters, of course. We've seen some very innovative solutions with the goal to make EVs more affordable, which I think is very relevant. Looking at the core topic, of course, where you're working in, I think Jenny, you mentioned that. So it feels like a spider diagram where you just increased all the axes. So that's we have very tough goals here, of course. You were talking about digital twins to improve the efficiency, not just on the hardware side, but also on the control side. Also, I think we've seen some very interesting solutions to also improve the circularity so that we design for recycling also in these solutions. So with that said, the floor is open for questions. And yes, I see a question in the middle.
Hello everyone, so my name is Wissam from IFPEN, a French RTO. So thanks everyone for the presentation, very clear, and I believe really that the set of KPI that you want to reach is very challenging. My question is on MAXIMA project. So you decide on your project to go with AXIal flux motor technology, which is a very innovative technology that we know all. But what about the price? You mentioned that it will be more or less a challenge to go to €6 per kilowatt, especially for mass production. Do you have any levers that you can share with us? How can you go to this target? Thanks a lot.
Sorry. Thanks a lot for your question. So what you said is really true. So it's about the price of the AXIal flux machine currently. But if you compare, in fact, if you look at the experience we have related to the manufacturing of radial flux machine, it's very large compared to the experience we have, especially for mass production for AXIal flux machine. So what I should say is that I won't answer to your question, I'm sorry. But what I should say is that we have still some work to do to improve, to reduce the price. But now we start to find some interesting solution. But I don't know yet if this solution will be, how can I say, sufficiently efficient to reach the goal of €6 per kilowatt. Okay. I'm sorry, but so just maybe one point. What is difficult is the assembly of the rotor and the stator. Especially if you want to increase the performance, you should go to very small air gap. Okay? So we can get very small air gap for radial flux machine, which is not easy for axial flux machine. So one main point currently for us is to try to keep the air gap small, and it's not easy.
Yes, thank you for the answer. There were more axial flux machines in the presentation, so anything to add from the other presenters on that topic?
Does it work? Yeah. Yes, I can. I know AXIal quite well because we have a good collaboration with them. Getting the cost to an acceptable level, in this case, the €5 per kilogram. Well, they know, they have a lot of experience in suppliers and so on, and they're very confident that this is a realistic level. So not only for automotive applications, but even for industrial applications, axial flux machines, let's say in bigger production volumes, can compete the prices of radial flux machines. But it's just a matter of supply chains.
Yes, thank you. Any additional questions from the, oh, more hands, okay. Yeah. Then we start here in the front, maybe.
Thank you very much. Eric Amago Innovate. Question with respect to a digital twin and so product passport, or so an innovative business model. How do you see here the possibility, opportunity in terms of innovative business models, Second Life, and so product passport? I think.
Is it? No, it's working. The main idea is like that, because we put those valuable resources to the motors. It's likely that we, to a certain extent, try to use the rare earth permanent magnets, unless there are some innovations that allow us to get rid of completely of the rare earth elements. But anyhow, we put those elements in the motor in the near future, and it would be very good to understand like what is there when we are in the phase, like when we start to dismantle, because then we could use the valuable resources the best possible way. So this is my very simple explanation for that, that if we understand what there is in the motor to sufficient level of detail, then we can more efficiently reutilize the material, whether it is more energy intensive recycling, or is it a reuse or something like that. And I wish that after the end of these projects we could generate this kind of information for everybody to be used from these experiments that we do. That what is the grade of the magnets, what is the quality of the magnets when they come out, what is the quality of the magnets made of recycled rare or the powders, or how do you want to call them. So this is my answer, but how about my colleagues? Do you want to amend something?
So maybe just to add something about what is interesting with the digital twin is that, as I said before, you can access to almost everything inside the machine. So for example, you can have access to the temperature in the winding, but very accurately. So it means that since the temperature has a great effect on the insulation and the aging on the insulation, it means that collecting this information, so during the life of the electrical machine, at the end of the life of the electrical machine, for example, when the vehicle is over, and you have exactly the health of the electrical machine. And so you can predict what we call the remaining life of the electrical machine and use it again, okay? And so this is something that is not available now, but with digital twin, it will be. So this is what I wanted to say in the presentation. You can do the same with the magnets, okay? You can do the same with other parts of the electrical machine. The bearings also are very important, because if you look at the failure, in electrical machine, bearings are very important, and so like this also you can monitor the constraint that are experienced by the bearing, and like this, at the end you can also evaluate the remaining life of the bearing.
So now it works. Okay. So I think there was a question also on the second row here.
Good morning, this is Germano Soro from CINEA Automotive. Congratulations everybody. I have a question for Martin. In your presentation you showed an image of your in-wheel motor solution, and I had the impression that the knuckle you considered was made of aluminum instead of iron. I assume that was for weight purposes, but considering the weight you have in an in-wheel motor solution, I would like to know, did you consider what manufacturing technology was? Gravity casting, it was low pressure, or it was forging of aluminum needed? for that solution? Thank you.
So thanks for the question. It's indeed a very detailed question. I have to forward this to the colleagues from University of Bath who do the complete development of this, and Elafe, of course, did the integration. But I think for the prototype, at least, I can answer the question that it's aluminium alloy that is milled and perfectly fit into this constraint. So if this answers your question, but we don't know exactly. Well, we are trying to squeeze it down a little bit, of course, make a smaller out of it. So if you have further questions, I'm sorry, I cannot give you the details that you want, but I will take the question and will forward it to our colleagues. Sorry.
Then there's a question in the back.
Good morning, everyone. Adelaine Ben-Kenida from IFPEN, French RTU. My question is on the EMTech project. To my knowledge, AXIal flux technology is more suitable if we would like to reach a high level of torque density. So can you please explain why you choose a radial flux technology for in-wheel motor? Is it a question of balance between one motor from one side and a motor reducer from the other side? Is it a question of cost? Can you please explain a little bit why it's a radial flux technology? Thank you.
Another very good question, so of course, so we have more or less a little bit older starter for SME as Elafe for the in-wheel motors. So I'm sorry again, I have to forward this question to our project colleagues. So I don't have the right answers, especially for this broad variety of audience. I'm sorry for that.
Mm-hmm. Yeah, thank you. I think there was another question by Simon here in the front.
Thank you very much, Damian. Good morning, everybody. Simon Edwards, Ricardo, but asking a question on behalf of Le Mesuré and 2.0, I guess. But first of all, I think partly as responsible as the web designer, as Damian mentioned for this call, I appreciate the work that everybody's doing in responding to the call. It's very difficult, so much appreciated. We heard from Jenny about the CO2 equivalent saving over the life of the motor, I think 582 tons of CO2. And we also heard from, I think it was Stefan, about 32% reduction in CO2. So my question is directly to you, is that CO2 equivalent or is that CO2 just over the WLTP with a hybrid machine? And then secondly, can any of the other projects comment on a CO2 equivalent saving over the lifetime? Thank you.
So I'm sorry, I'm not a specialist of LCA analysis, but what I should say is that so the 32% were related to CO2 equivalent. Okay. And what is interesting in fact in this analysis, I will repeat what I said just before, is that if we go to an electricity mixed that is totally decarbonized in the future, it means that manufacturing will become the main source of emission. And so what I presented didn't take into account the recycling. So it means that with the recycling, you can still improve or to reduce the CO2 impact also.
Could you give me a second so I can be a bit more specific? I will check because this number that it was on the impact slide, yes. Right? So could you give me a second how that was evaluated? So it was what it was, but I think we evaluated in the proposal preparation phase, like for the lifetime for certain set of vehicles on the market, and that could be the total outcome reduction.
And that was fine.
Okay,
that was good.
Very good.
Thank you very much for that.
Okay.
I was just wondering whether any of the other projects had done something equivalent or were planning to do something equivalent. So we've just heard from MAXIM project. I wondered about the others. Thanks a lot. But let's carry on.
So, are there any additions to the savings, CO2 savings? If not, then are there any additional questions if we don't have CO2 savings now? Yes, in the second row.
Yes, Rod Franklin from CUNA Logistics University. I have a question. Either you looked at radial or axial. Has anybody looked at the hybrids that are now coming out between the two as a potential? Because there are hybrid versions, and I'm just curious. So that was my first question. And the second is in controlling technology. Has anyone looked at now the evolving AI as opposed to traditional closed loop control systems?
I can comment a bit. So regarding the first question, not in this project, but I know of other European project where the hybrid, maybe you are referring to transverse flux machines or combination of those, they are being investigated. But then you may introduce other challenges regards to manufacturing. So how you then most efficiently make the soft magnetic cores for such machines. So maybe here, because we needed to screen the the price also so much, we couldn't like dream on very much on that aspect. But this is a very nice question. And I actually have one question also, but maybe we take first the questions from the audience and then. And regarding the control, that's also very nice. And I think something wasn't it towards that direction that you presented?
For our case, it was mainly during the design phase that it's a reduced order model that we made over there. But it's not really in the real-time controller itself that we're using AI. Well, I know that for controller tuning, we do use at our department, reinforced learning techniques to optimize the low-level control even. But it's not yet, it's not taken another part of this research over here.
So maybe an additional comment from my side. So from MTech side, hybrid, to answer the first question, hybrid was a topic, but of course all the companies that are involved has decided to go in the specific technology. And on the second topic, so AI in control, there is something what in specific AI comes in place. And we try to have some kind of reinforcement learning implemented in overall structure of vehicle, global vehicle control. And that's something we really want to force in addition to this to MTech project and other projects as well. But there is a lot of, if you read through the AI Act, there has to be a lot of testing as well as a lot of safe fail modes to implement it so that the AI works pretty fine in some control units which can harm people or other public. So that's a very interesting topic, and I hope a lot of calls to this topic will come out soon.
So again, I will come back to the digital twin. So in fact, in the digital twin, so as I mentioned, so you have different kind of models. So you have an electromagnetic model, the thermal model, and so on to predict the temperature distribution in the machine, for example. And so the construction of this model can be done either, as I said, by using techniques like, so you start from the high fidelity model and then you use some mathematical technique in order to reduce it, to have a very small model but very fast. Or what you can do is to use the data provided by the high fidelity model. And from this, you use this high fidelity model to train artificial intelligence system. And then like this, you can have a model based only on the data. The other model I was talking about from using reduced order model are mainly based on the physical approach. And then you will have to, how can I say, to recalibrate, as I said, from data you collect from the real device. So this is something that also is important because you have always a bias between the device and its digital twin.
Yes. Yeah. Just to comment, our idea was more or less the same. We have been developing the digital twin, and our idea is with experimental data, just to try to recalibrate the system at the end, yeah? But nothing more than that. Just to comment.
All right. I think there was another question on the left, or is that already answered? Yep. Okay.
Jeremy Warren from AP Plus Laboratories. First of all, I really appreciate all the presentations, very fascinating, and I appreciate the complexity of what you're addressing. I had a question related, it's especially for the clustering. So all of you are working on all of these digital twins and all of these approaches. Is there going to be an effort moving towards the latter part of your projects to approach or to find commonality in your digital twin approaches, or to share and collaborate in order to build something more transverse between the projects?
There is maybe only one correct answer to this, and that is yes. So how that could be realized, that's another question. But definitely, like this is something that we should, of course, target at. And your question and comment was very good. Of course, there might be some challenges, like related with the platforms, confidentiality, IPR, not, but very good comment.
It's okay.
Maybe to hand over the microphone to Eric Amongo, who is more or less leading also the Evolve cluster, wants to say something about this topic.
Thank you very much. If I may comment so this aspect, because this is a very key aspect. Confidentiality issue is a key aspect which here's some hindering in so really openly as exchanging this aspect, but a very important part as well. So what we are trying to do is a common joint publication, and we had here in the ISM project, so in the ISM conference with the support of VOLTCAR, so already a common publication. So we will have here for the SI World Congress as well, so a common publication trying to identify those topics of common interest, those synergies, those complementarity in order to push this aspect. And we are very welcoming those topics of common interest so that we can prepare our next common publication, which will rely on the contribution of the partners of the different projects under the understanding what we are allowed to share and what are confidential information. But we take this input as a very important aspect. I think the topics of recyclability, this is as well a second topics of common interest, and we are welcoming other requests to have some common statement in this direction. Thank you.
All right, very good points. So are there more questions in the audience? If not, then you, Jenny, there's, sorry, I didn't see you, Ian.
Yes. We are missing a question from you, Ian.
Hello, Ian Pfeifenbosch. I have one question to HEFT. You're proposing to use or using a plastic housing. And from my knowledge, a plastic housing would require, say, a duroplast. Is that compatible with recycling?
I'm not an expert in the housing, yeah, because it's going developed by Sumi, the company, yeah. But I know at this moment they are working with that, but that the plastic is not recycled at this moment. Yeah, that was one of the questions. Yeah. Further than that, I mean, we have do the housing based on the requirements of, in this case, that was the tier 1. So I suppose that everything goes okay. But at this moment, they are working on that. But at this moment, it's not recycled. Maybe in 2 years, yes, because they are working with that, but not at this moment. Yeah. But maybe Javi, that is from the project, he has more information. Yeah, he's asking for the microphone. Okay.
Yes, nowadays is a thermosetting. The manufacturer says that nowadays is not recyclable, but they have a study that the LCA of the plastic housing is less than the aluminum housing for full system. Nowadays, the plastic is not recyclable.
Okay. Then I would hand over the question to Jenny. You already said you wanted to ask something.
If that's okay, I think that was very interesting that you in MAXIMA, you are working with the soft magnetic composites as well, because one person wiser than me said some time ago that many innovations in the electrical machine industry have originated from new materials, new material compounds, from new manufacturing technologies and things like that. So what is the benefit that you are targeting at with the soft magnetic composites?
So what is interesting with soft magnetic composite materials is that you can manufacture complex. So the first thing is to manufacture complex shape. But you have limitation, but complex shape of poles, for example, of teeth and so on. So and for mass production, it can be very well adapted. Nevertheless, because we have in the project one electrical steel manufacturer and one soft magnetic composite material manufacturer, I should say that until now you have advantages in both solutions, and so I should say that for the manufacturing currently we can say that maybe soft magnetic composite material are very interesting, but as I said before, I think that there are a lot of things to do for manufacturing, to develop new manufacturing process for axial flux machine, for mass production, which are not available now and which we'll have to develop in the future. So I don't know if I answered to your question.
Right, thank you. Then we had another question here in the front, actually, towards the plastic housing.
So this is also for HEFT. So it was already mentioned, the lower LCA. But my question is about what is the approach for safety and for stakeholder acceptability? So you are telling to people, okay, it's a plastic motor or plastic housing motor. How do you see the acceptability and how do you deal with the safety concerns?
Okay. I don't have too much information about that. Maybe I will tell you later on. Yeah, I mean, once we speak with Sumi, I mean, at the beginning of the project, we provide all the requirements of the housing. Yeah, based in that case was a tier 1 in the project. So we propose all the requirements, and they have been doing research just to find the, let's say, the suitable plastic. Yeah, yes, because maybe I'm using plastic work and it's not the proper one. Yeah, so I understand that the performance of that housing is, let's say, equal or very similar to the one of the other materials of aluminium. Yeah. About the recyclability, I have said before, yeah? At this moment, no. It's not. But I mean, now at this moment we have to do some prototypes. But the idea is that in the following year they are going to try it. They are doing research in that, just forgetting it. Yeah. But I mean, I can check later more information about that. But I assume that the performance of the housing is similar to the one, at least of aluminium, of other materials. Yeah. Okay.
Yes. Thank you. Are there more questions from the audience? Yes, Wissam.
I promise it will be the last one. So, last question. I understand that this call is really focused on the electric motor, but in the electric vehicle we have electric motor and power electronics, and mainly when we have to compare performance between different, let me say, power traction motors or power electronics, we need to also integrate the electronics. When you do testing, or when you also communicate on performance, especially I was thinking about HEFT project, when you compare with Fiat 500, the car, are you taking also into account the constraint that they have on the power electronics, mainly the current, the voltage? Are you comparing at the same level of voltage with the same power electronics, or we don't have, or we didn't integrate this, let me say, constraint on the power electronics when you design your electric motor? Thank you.
Okay. I mean, the values that we have at the moment are the base of the design of the electric motor. So it's limited to electric motor. Yeah. We don't have further information. I mean, it's in some cases it's because we have coming from the tier one, we have information that is already published, and we have compared with that one. Maybe I can say that maybe in the 100% is not right, yeah, because I mean, some information maybe is not published, but that is just focus on the electric machine at this moment, yeah. On the other hand, in the case of the digital twin, we are analyzing, yeah, both battery and efficiency of inverters. So with that, we will have more information. But I mean, the results that I present are limited to the machine. Okay.
Well, in our CliMAFlux project, there we have a direct involvement of the power electronics in the motor. So we're making a full IDU, so meaning power electronics that are integrated with respect to electromagnetic part, but also thermal aspects and so on. The inverter there it's an 800 volt battery system that we're considering over there, so meaning 1200 volt components, more or less standard 2-level layout. But in a new project there we are actually want to, again, the person points additional, and then we are going to take a look at multi-level technologies. So multi-level technologies, certainly for AXIal flux, might be beneficial. Let's say starting from a voltage level of 800 volts, but also, and for sure, with the new upcoming 1200 volt battery systems.
All right. Any additional questions from the audience at this point? If not, then I would take the chance to ask a question as well, and to all the projects here. So we've seen some very innovative solutions with axial flux machines, with in-wheel motors, direct cooling. The question is a little bit not specific to your solutions in the electric motors, but beyond. So do you see any adaptations needed on the vehicle side to include your solutions from the project to make them feasible in the vehicle? Are there any challenges that you see to include them?
I will try to explain. So what I should say, as far as I understood, so I don't know what is related to market, automotive market, and so on. I'm not a specialist and about the final customer, the client, and so on. But until now, so maybe there are OEM in the attendance, and maybe they can add some information about that. But what I should say is that until now, I think that the specifications of the electrical machine are mainly pilot or given by the client. For example, if you look at why do we have peak torque and continuous torque, is that because the client, I suppose, the client wants to have a car that speeds up very quickly and so on. But maybe from the environmental point of view, okay, there is something to think about, so to have new specifications more related to environmental impact and so on, and not necessarily related to the client need. But for that, we need maybe to educate the clients and so on. So I don't know, I have nothing to say, but nothing more to say. I'm not a specialist, as I said, but I think the specifications maybe could be modified in order to have more, how can I say, devices that has less impact, less environmental impact.
Maybe also adding some points to that. So we are also developing an in-wheel motor. So this is something very special due to specifications. So we need a quite large rim to fill in the in-wheel motor easily, because to fulfill then the specification from the OEM. But on the other side, there are a lot of benefits if you use the full broad variety of control strategies with torque vectoring and so on. So you can really dig deeper. You can easily adapt or easily exchange this in-wheel motors. You can really put it on different vehicle segments, especially if you have the specifications met and the rim size. Yeah, there is quite new ways to think about new possibilities and adapt, and new vehicle segments as well as new vehicles as well.
But to give an answer why AXIal flux isn't yet there in mass manufactured production B-segment cars, there I think the issue is that AXIal flux technology relies on quite novel technologies, like there are a lot of epoxy overmolding or overmolding in general, new production technologies, specific ways of sealing parts, specific ways of cooling with microchannels and all these spots. And if OEMs, they really want to introduce such a product on the market, they're quite aware that if something fails or if something is not fully developed yet, then you end up with huge recalls and actually making your company almost bankrupt. And therefore, I think, and that's the reason why, for instance, YASA, the big competitor of Magnax, is really working together with high-performance cars. So there, let's say, the risk is less, because, let's say, a lot of these vehicles are just made to test them until they fail, just to get the ultimate performance, but not to last for 8,000 hours or more without any failure. And I think this is, as I hear, still the biggest issue. It's not the production cost; it's really the reliability, and it has to be proven on a wide scale before it can be implemented in cars.
On the part of VOLTCAR, I would say that from mechanical perspective, like if you think it should be quite easy-peasy or business as usual, we are actually mounting the VOLTCAR motor inside of an integrated unit frame or housing of a project partner. So in that respect, it should be quite straightforward. But of course, we have the direct liquid cooling system, which introduces some additional task to integrate with the overall cooling management system or the thermal management of the vehicle and its components. But this is the first thing that comes to my mind. Is this?
Okay. Just to comment in our case, in the case of HEFT, I mean, all the requirements and specifications have been done by a tier 1, so we understand that the machine that we are doing is suitable for the market, yeah? Apart from that, I think that this is a project with a lot of innovative challenges, so we don't have to limit just to the prototype. I think that it's important to keep in mind that many challenges have been developing in that project that can be used in another prototypes, another motors, let's say. Yeah? So just to keep in mind that it's not just the prototype, it's the innovative challenges that we are going to solve. Yeah? Thank you.
Yes, thank you. There's still time for an additional question. If there's someone from the audience still has an urge to ask something. If not, then I would suggest that we take the chance to post your questions in the coffee break that we'll have now, so that if you have any question that you want to ask directly to the speakers. Yes, thank you to all the speakers who participated here. Thank you for all the interesting presentations. Thank you, Joao, for sharing us here, and all of you for your interest in this topic. I hope to see you again in about half an hour for the next session for innovative components for EVs. And yes, see you soon, and have a nice coffee break.